Welcome to today's presentation about stitching. So, quickly about the outcome. First, we look about what do we mean by stitching, then the positioning challenges, the difference between active and passive stitching, some layout considerations, then some applications and results, and a conclusion at the end. So, the NanoFrazor system has multiple stages. So we have on one hand the coarse positioner with a range of 100 millimeters, and we have a scanner which we do the fine scans. So the scanner range is limited to about fields of 50 by 50 micrometers. So when we have a bigger layout, we need to stitch it together in multiple fields. That's what we call stitching. So we split the layout into multiple fields and write them after each other. This brings some challenges. Because we have multiple positioning systems, we also have multiple coordinate systems that really need to match each other. So when we move with the coarse stage, we shift our scanner range, and if we do not move perfectly, there will be a small gap between the two. Or it could be an overlap or some shift in both directions, and then your tiles would be messed up. So where do these errors come from? So we have on one hand just the repeatability of our coarse positioner. This is quite good with around 100 nanometers, but still you would see this. Then there can be some systematic scaling errors between the two coordinate systems. This is typically less than 0.5%. And there can be some relative rotations between the two systems. Also, this is normally in the order of around 5 millirad, but they exist. And overall comes thermal drift. So if your temperature is not stable, the systems will drift away from each other. So what is now the difference between passive and active stitching? The normal mode we do, like if we do not specify something special, is called passive stitching. So when we have a design that is larger than our scanner range, we split it up in multiple fields, and then we just write the first field, move to the next position, write the next field, move to the next position, and write the next field. And as I've shown you before, there can be these errors between the fields, so it's not guaranteed that the layout is perfectly aligned. So for this we have a solution which is called active stitching. You can activate this in the world map. So the workflow here is a bit different. So as before, we write the first field, but then after we move with the positioning system, we read again a small part of the previous field. And then from this we can calculate some offsets, like where we think we are and where we actually are at the moment. And we can compensate this really small offsets. And then we write the next field and so on. So again here the workflow, so we pattern a field, we move to the next position, we read again a small part of the previous field, calculate the shifts where we think we are and where we actually are, and then we align the next field automatically. This offset calculation is done by some image processing algorithm, and we have a sub-pixel accuracy. So the pixel space is dependent, or will give you also the accuracy in nanometers. So if you have a high resolution layout with, for example, 10 nanometers pixels, you will also have a better alignment than if you have bigger pixel sizes, because it's always linked to pixels and not nanometers. But here we see an example on the left where two lines were stitched together, and just by eye you cannot see the difference. So it's below 1 pixel, so in this case it was below 10 nanometers. So why don't we always use active stitching? The thing with the active stitching is, since we need to read again these fields in between, it will take longer. So if you have a simple layout, you can just specify an overlap between your fields that you have split, and even with some positioning errors, they will still make contact. So in this example here, you see on the lower right the shifted fields. Because of the overlap, they will still be connected to each other, so you do not need to do the active stitching. The active stitching is needed when these positioning errors are not tolerable. So for example, if you want to do holograms, lenses, waveguides, so where it really is important you match it up to some nanometers. It's also important when you have like a big lattice or an array of some structures that is bigger than your scanner and you want to keep the constant pitch. So also then you can use the active stitching to guarantee this. So again, here is a quick comparison between this dummy layout from before. If you use the active stitching, it will take, in this case, 50% longer, so up to 1 hour more. So this depends on your layout, but it can really be a loss of time. So you need to decide, is it really important that I do this? Then there's also some limitations still. So if you pattern like a closed loop of a target, even though we have nanometer accurate stitching, after lots of fields, this still can grow a bit, this error. And at the point where you connect your loop, there can be a small shift. The same goes if you have multiple starting points. So in this example, like you start with the red line and then in between you jump away and start at the purple line, and where the two paths meet, there's a really small gap in between them. So you need to watch out that you do not start at multiple points. So when you load in a layout in the importer of the NanoFrazor, it tries to make as big as fields as possible, and also by default just orders them in a raster. So you see this in the example here. It makes big fields and it starts on the lower left, goes to right, then jumps to the upper left and writes again from left to right. So this will result in a closing of these two loops at the rightmost point. So if we would change the splitting size manually a bit, we could actually improve this target. So we make the field so that this first loop is stitched in one part. And then we reorder the fields a bit so that we do it in one line and will not have a place where the two paths meet. Like changing the order of the fields is quite simple. You can just drag and drop them around in the world map. So let's see some actual applications. So a nice result we did back in the days was a hologram. This is existing out of 100 fields, and they were stitched together, and then at the end you can shine a laser on it, and it resulted in the old company logo. So again here, this was quite a big design, and it took over 10 hours of patterning. Another nice design is some more recent, some electrodes where we needed this constant pitch. So we had to split the fields up into 4 single fields and stitch them together. And after developing, we saw with the SCM Like it really stitched it nicely together, so you do not see where one field ended and the next field starts. And then I also have this waveguide from before, from the layout. So we patterned this on a high resolution stack. So on the left you see an AFM image after the patterning, and where the arrows are was the stitching done. And on the right, also after development, you see it was connected seamlessly. And here a last example, this was an array design of some small windows, and again it had to be split up into 4 fields. And on the right you see the microscope image of the 4 fields stitched together. So as a conclusion, if you have simple designs, you can just specify an overlap and do not need to use the active stitching, because the active stitching takes longer. But if you really need seamlessly stitched designs with nanometer accuracy, you should use the active stitching. But also, if you do active stitching, keep in mind you maybe need to adapt your splitting size and the order of your fields to get the best results. If you want some more information about active stitching and overlay, there is a webinar on YouTube which you can check out. Thanks.